Okay, let's get started. So today we get, I guess, start another sort of really important topic, which is finally addressing the fact that our real systems have noise, and we don't know them perfectly. We've talked a little bit about robustness throughout the time, but today I want to talk specifically about model systems that have stochasticity baked in. Okay, so we've made it this far thinking about the world as x dot equals f of x u, or in discrete time, which we'll do more of today since a two-lecture sequence on stochastic processes, everything's easier in discrete time. So what we want to do today is now think about the case where suddenly this has got to describe a stochastic process. And typically we don't do that by hiding some stochasticity in f. Instead we're going to write it as x dot is f of x u plus some external input w, or in the continuous, or in the discrete time case, like this, where this w here is some signal, is the this is the output of some random process. Simpler random process, right? Maybe it's a Gaussian or something like that. Okay, so we're going to be very explicit. We'll leave our f mostly alone, but if you could think of that as being, for instance, a disturbance force, right, that's coming in as an extra input into the system. It's actually very general, right? So Wt could be an unknown parameter, right? It could be the unknown inertia of my quadrotor, in which case it might not vary in time, but this certainly captures the ability to vary in time. And you can imagine writing the equations down with a w, right? So the inertia is my estimated inertia plus w, and that would certainly fall into this sort of description, or it could be wind or something like this, something that is really naturally time varying, and putting in a force, a time varying force on my quadrotor or something like this, right? So it's a very general form. One thing I'm not writing down explicitly yet with this is typically called the sort of process noise, right? And I say that to distinguish it from measurement noise. We're still not talking about measurement models or sensors yet. Not because they're not interesting, but just because there's enough to discuss here first. So actually, there's lots of good classes and people who work on here on state estimation, on planning under uncertainty, on all these topics. And typically, the measurement model is extremely important to that. But I hope to convince you, I'm going to give you the sort of dynamics and control view of stochasticity, where the focus is on the process dynamics and the process noise, just the way uncertainty from process noise in this case, propagates through a dynamical system. Measuring it is a second step, and we may or may not get to that. See how far we go. Okay, so I'll just say as distinct from, although conceptually very similar to, measurement noise. And you can argue whether they're actually distinct, because you could write closed-loop systems in this form that have measurement in the middle and everything like that. But I want to emphasize here, you've got a dynamical system with some noisy disturbances attached to it. Okay, now, so again, this is a very general form, possibly to a flaw. So a lot of times we'll have an important special case. Would be if that omega, or this noise, sorry, just W, comes in as an additive noise, right? So a lot of things will be nicer if we're willing to have, if we are able to write down the effect of that disturbance or noise on our dynamics in an additive form. It's not always required, but that's an important special case. Okay, so I like to start with a really simple example because I think you may already know the answers, but I think it's helpful to just put it into the view of the class here. Okay, so as soon as people look like they're done writing, I'll switch here. Okay, so here's a real simple example. Call it a particle in a bowl with Brownian motion. Okay, so I want to think of some sort of bowl. By bowl, I really mean a potential well. Okay, and I've got some ball rolling around in here, which mostly goes downhill. Okay, but it's going to be there's going to be something that makes it bounce around a little bit, like Brownian motion. Okay? So I'll write the dynamics as I'm mostly where I was before, but I have some dynamics that drive me down the hill. Right, that's my potential contribution. And then I've got some extra additive noise, which is going to be the source of sort of a Brownian motion. Okay, and the most natural and algebraically simple form for that potential well would be if I choose u of x to be a quadratic. We'll generalize that in a minute. And in that case, you could think of this as a lot of different ways, right? So you can get a quadratic potential, for instance, out of a linear spring, right? So you could think of it also as even a mass on a spring, right? It's just like a linear spring would give us that sort of a potential. Okay, so yeah, so if I take the gradient of that, of course, I just get alpha x. So if I put this dynamics together, I now get the dynamics 1 minus alpha x n plus wn. All right, so this is a linear system. So you certainly know how it behaves when W is 0, right? You might know how it behaves when W is non-zero too, but certainly for if W is always 0, then we understand everything about this, right? The long-term dynamics are just like this. It's the discrete map, right? But it's just a linear system. So what is that? That system has a fixed point at x0 at equals 0, and it's exponentially stable if alpha is, well, with the 1 minus alpha here, alpha has to be in between 0 and 2. Okay, that's just the simplest possible sort of one-dimensional discrete time linear system. Okay, so we're going to come back to that, remember that, make sure that our stochastic analysis makes sense relative to that. But let's think about what happens now if W is not 0, okay? So the other common choice is to choose Wn to be drawn from a Gaussian process, right? From let's say a mean 0, identically individually distributed IID process of Gaussian white noise, right? So that means the mean 0, I'll use the notation, the expected value notation like this. The expected value at any given time is 0. And then the IID assumption I'll write down as the variance is almost always 0, but we'll call it sigma squared if I equals j and 0 otherwise. Okay, so where sigma is just the standard deviation. So the notation might be slightly different than what you're used to, hopefully not too bad. But all this basically means is at every time step, completely independent of anything that's happened before, I'm going to pick W by calling rand in MATLAB, right? And that's all this means, right? I get a 0 mean Gaussian random variable independently drawn from every time step. Since it's a scalar, this is, yeah, it's just a variance, which I can write like that. Okay, so now the question is, I've got now a stochastic differential equation, right? So what do we do? Well, difference equation. So, our standard difference equation question would be if you give me x0, right? What is x at? Or what is x at infinity? Right, these are the questions we'd like to potentially try to answer. Maybe they're the wrong questions. Right, but we'd like to somehow talk about the long-term performance of this now random, the stochastic system, right? The problem is now xn, right? So x0 is given in this case, but xn is now a random variable. So it's not as meaningful to talk about, what is the value of xn or value at x infinity. You have to somehow ask about the properties of the random variable. Okay, so instead, maybe we need to describe the probability distribution and say probability distribution. Right, and our goal will be to understand the dynamics of that distribution, right? We want to somehow say that, well, if I've got a stable system, I'd like that the probability distribution, that there's the high probability that I'm near the origin or something like this. We want to develop, that's the goal for today, is sort of develop the language of talking about what happens to this random variable, right, over time. And how can I build a controller that's going to somehow shape the dynamics of that random variable, right? Maybe give strict guarantees that that random variable will never be in a place that I don't want it to be, right? Those are the questions. What tools do we have that we've already got in our toolbox or that need a little bit of extension to address that extra complexity, right? Okay, so the cool thing is, given the equations of motion, we can write down the dynamics of this probability distribution, right? In stochastic processes, you might call it the master equation, or there's various names for it. But I would like to write down the dynamics of that distribution, right? So I'd like to see how this evolves as I change n. Okay, and I'll give you pictures to hopefully that'll make this really clear in that example. But how many people feel like, oh my God, he's talking about probability? Or how many, let's ask that question. How many people don't like probability? That's a fair question, right? Yeah? No one's going to answer that question. How many people are completely comfortable with probability and random processes and don't need to hear this? Okay? Awesome. All right, so somewhere in the middle. Okay, let me try to tell that story. Okay, so I want to write down somehow. Right, this is just some function that is now, it's a function of time, right? And I want to write down its dynamics, the dynamics of that function, of that probability distribution. Okay, and that's a crazy thing to think of the first time, but I think it's very natural, and maybe you've already thought about it if you've thought about estimation or planning under certainty or anything like that. Okay, so it happens for the linear Gaussian case. It's very easy, right? So I'll show you a few of the mechanics just so there's no mysteries here, but hopefully they're not too bad. Hopefully they're either familiar or not too intimidating if you haven't seen them. So in order to write down the dynamics of this, I'm going to have to do it in stages. The first thing is just to write down my Gaussian in this notation, right? So the probability of a random variable w at time n equaling some value little w is just my familiar Gaussian distribution, zero mean, okay? And then this will tell me actually what the process dynamics look like. So the way I want to write that down is I want to figure out the conditional probability here that xn plus 1 equals some value, let's call it y, given I knew what xn was, call that x. Okay. This is now, if I knew what x was at time n, I have some distribution over what it's going to be at the next time step. And that distribution, oh, sorry, Juan, yeah?
So that's the probability density function, right? Not the probability that it equals a certain value.
This is the density function, yeah.
But on the left-hand side, it looks like it's a probability that noise is a certain value, which is 0.
I think that's just correct. Yeah. I think you're thinking of the cumulative distribution. If it was less than or equal to, then I'd have the extra thing. But this is actually the probability that it equals some value.
The notation makes it look like there's an event that y of n is equal to y, and that event itself has probability 0.
Yeah.
Okay, so you don't like the fact that I've got an in here that this. But I'm going to call my random variable here omega n. So I have some random variable which takes on values. The probability of it taking on value 0 is like this, and so on. Yeah. You don't like the notation?
It's a density, not a probability.
Yeah.
It's not a probability of mass.
Is it a discrete variable or a continuous variable that makes the problem? Because if it's continuous, then the probability of it being included or being 0, and if it's discrete, then it's something, which is, I think, the problem.
Okay, cool. So this is, it's discrete in time, but this is a continuous distribution, right? So little omega is a continuous value. Little w is a continuous value. Yeah? So don't let this, don't let that the fact that it's discrete in time confuse you. It's absolutely continuous. It takes on continuous values, W. Yeah.
I think if you wrote like little p instead of PR, I think that would be different.
I see.
Yeah.
You'd rather me write little p? Good. I'm happy with. I'm okay with that. Okay, so the probability of y taking on some value, given I know x, is just, well, it's a combination of my dynamics and this noise, right? Right, so I had that, and if I change my notation using y and x, I had this. That was my dynamics before, right? So I'm just writing it using my y and x notation here. So now this is y minus 1 minus alpha x. Okay, so it's just some now Gaussian with a new mean at 1 minus alpha x. Okay? Right, so this now gives me the dynamics of my distribution, right? So I can write down some update dynamics over the domain of omega, let's say. Which is that probability of y given x times the probability of x. Call it dx here, like this. Yeah. And I can update my dynamics now. I can update this distribution. This is now my governing equation, right? This probability update. And this gives me a dynamics which takes me from probability of x0 equaling some value, and I can evolve that through those updates to probability of xn equaling some value, right? Just by repeatedly applying this equation. Yeah? Sort of makes sense? Sorry if my notation wasn't good enough. Okay, so in the particular case of this being, Gaussians, right, this is basically a convolution, right? It's not quite a convolution. There's no sign, but we know the properties of taking an integral over two Gaussians multiplied by each other and things like this. This is something you've probably seen before, but it happens that there's this magic that happens if I put a Gaussian in here, or even first off, let's think about if I have known initial conditions, right? So right, so what would known initial conditions mean if I started my system with absolutely clear that at time 0 x equals x naught? In probability, I could write that as the probability of x0 equals x is some delta function. Right, some Dirac delta. If I convolve a delta with any signal, if this is now taking me back to 6003, for instance, okay? If I convolve a delta function with a Gaussian, what do I get? If I convolve a delta with any signal, I get that signal back, so I get a Gaussian back. So after one step, I'll get the probability of x1 equals x is some Gaussian. And then it turns out if I convolve a Gaussian with a Gaussian, I'll get another Gaussian. So this thing stays like a Gaussian, okay? And what's awesome is that all these things in the simple one-dimensional case, you can do a nicely enclosed form. It turns out that, that this dynamical system of the probability has a steady state solution, okay? Distribution, right? And it's a Gaussian, right? What do you think the mean is going to be of that Gaussian? 0, right? This is the probability of x infinity equal x, let's say. And it turns out that the variance of that distribution is sigma squared of my update, my noise, 2 minus 2 alpha squared. You look at this sort of, when does that even make sense, right? You don't want that to hit 0, right? This happens to be well-behaved. When alpha's in the range of the original stability of the system. Otherwise, it's poorly behaved, okay? So that's the mechanistic view of it, but I want you to have the cartoon view of it in your head too. All right, so I have my potential well like this, right? And I start off with some initial distribution, let's say at x0, right? After one step, the mean is going to move like 1 minus alpha times that mean, so it's going to move towards the origin. And it's going to become a Gaussian, right, with sigma from my noise. So after one step, the process noise is going to spread out my distribution to be something like this. Okay. After a second step, I'm going to convolve my noise Gaussian with this distribution. My mean is going to move down like 1 minus alpha again. Right? I'll get something like this. Say. And what's magical is that this dynamical system reaches a stationary, has a fixed point. And it ends up converging to a steady state distribution like this. Okay, where we know we can compute exactly the long-term, the distribution of the steady state. It's beautiful, right? It's actually, I love dynamics. I love, pendulums swinging around. I love how they move through space, all these things. This is just that story, even better, right? So now I have an entire distribution that floats around with my complicated dynamics, right? Right. The dynamics of my system, my choices for the control, if I'm able to change with my control the shape of this potential well, right? What am I doing? I'm not guiding a single solution through the system to where I want it to go. I'm trying to shape an entire distribution as I go, right? I really want you to think about the propagation of uncertainty through the system as this just richer dynamics for which your goal in control is to shape that distribution over time and the time evolution of that distribution. Okay, so I mean the equations here are simple. They're well known. They're the if you've ever done filtering, this is the one-dimensional version of the Kalman filter with no measurements, right? This is just the linear Gaussian propagation, right? So the general form for a linear Gaussian system, again, no measurements, is if I have now a vector, a matrix equation, a multivariable linear system. Then my mean over time, right? And my xn is described by a distribution with a mean and in general a covariance. And this thing just propagates very simply through the equations. Even my covariance update is very simple in the no measurement case. Right, I always have to remember the discrete time one because I like the continuous time. The continuous time one, of course, is just is almost LQR's solution. These are again Riccati equations. Okay, but basically there's simple dynamics for the linear Gaussian case, which tell me how my distribution evolves, where now the distribution here is described by the mean and covariance. Okay, but you should just think of this as now another dynamical system, right? One that I can potentially control, right? Whereas originally, my original system, I was trying to control the state variables directly. Here, maybe I could try to control the mean and the covariance. And the goals for control should be to somehow shape that. Okay, so that's the linear story, which maybe is familiar. But are there any questions on that? No? It's an outer product for covariance. I see. Yes, I read it before the square brackets. Yes, it's on the second W. Yes. Okay, so now let's do the nonlinear case. Let's think about all the cool things that could potentially happen if I've got something more interesting than a quadratic potential. Yeah, and I can just, I can give you pieces of the story here, but it's a rich literature. Okay, so maybe the epsilon more complicated here. Imagine if I just made my potential well a little bit more interesting. Right, something like that. And I'll still think of it as a ball rolling down the potential. Now there's a really important point. Now, so just think about what this system might do if you have a ball rolling down here. Okay, in the deterministic case, I guess you can see it'll go here because this is a first order model of the ball here, so it's just either going to go here. Think of it as an overdamped ball, right? It's going to go here or it's going to go here, depending on which basin it is. Now I've added noise in, so everything gets much, much richer, right? So what could potentially happen? So, okay, so what we saw in the last one is it went down to the bottom of the bowl roughly, but it was bouncing around inside there, right? And I had some, if I looked at it at any time n, with n greater than, where it's mostly settled, then it's going to be somewhere around here. There's high probability it'll be somewhere around this origin. Right? Okay, what's it going to look like, do you think, as time evolves in this system? It'll be bimodal. There'll be there's some probability that it's here, some probability that it's here, probably more probability that it's here, right? But actually, if you look at the path of any one ball through here, it's arbitrarily complicated and rich, okay? There's people really talk about this example. Okay, there's the two-hump example, right? So the ball will go here. It'll get bounced around a little bit. It'll actually make escape attempts. That's what they call it, right? So every once in a while, the noise will build up, and it'll go here and maybe almost go over, and then at some point it'll actually escape and it'll come over here, right? This guy will come up and less frequently will make it up that potential and do an escape attempt like this. People talk about first passage statistics of that transition from one fixed point to the other. I mean, the dynamics of watching a single particle move through this are very rich, right? Lots of different things can happen. But the distribution, the dynamics of the distribution are actually very simple. Right? I'm going to have a simple convergence to exactly what you sort of expected, right? People talk about first passage statistics, all these things. It's a really important point, but the dynamics of the distribution are simple, really. Simpler, at least. All right? I end up with some probability mass at the end, probability of x at infinity equaling x is looking like something that has a lot of probability mass over here, and a little less probability mass here, right? It's really just a simple extension of what we've already solved. The dynamics are more complicated to write down because I can't describe them by just the mean and covariance. But if I could write down that function and describe its dynamics, I'd see it would converge nicely to this. In practice, we make some sort of finite approximation of it to do that, but you can see it even numerically. All right, so in general, these dynamics are dynamics of are now a partial differential equation because that's the dynamics of the function. Difference, yeah. But a lot of times we can get our head around it with some finite parameterization and some of our ODE tools, right? Okay, so that's our story here, is when can we actually reason efficiently about the way to propagate uncertainty through systems of interest, robots, complicated robots, maybe even robots that are making contact with the world, right? Okay, so my favorite example of this actually is if you think about a walking robot, I'm biased, sorry. If you think about a walking robot, and what's a reasonable source of uncertainty for a walking robot? Well, I don't know, wind doesn't affect me too much, I guess. What affects me a lot is the terrain, right? So imagine I have, I'm walking on rough terrain, and I can simplify the model of the terrain as saying, maybe someone is pulling terrain out in front of me, laying down the terrain in front of me from some, well, let's say a Gaussian distribution. Why not? That's sort of the friendly rough terrain case. Yeah. So can we think about even just the rimless wheel on Gaussian terrain? So it turns out the rimless wheel is a nice example because the rimless wheel doesn't have any selection sort of in footstep length. So really the slope at every, I could write down any sort of rough terrain, right? And I can describe that as it could be some arbitrarily complicated terrain, but if the robot starts here, it has a fixed step length. So it's going to step here, it's going to step here, it's going to step here, it's going to step here. Right? So I don't have to think about some complicated terrain distribution. All that matters is the angle of the terrain every time it hits, as long as I don't have internal collisions or something like that. I can really just think of this as a stochastic process where someone has chosen my slope of my rough terrain as an IID process on every step. Does that make sense? Right? So every time the robot takes a step, I have a different ramp angle. Right? And that actually, I could think of that as a ramp that goes like this, but it actually, any rough terrain for the rimless wheel looks like that. If that makes sense. Okay? All right, so you know what the deterministic return map looks like. So I'll write it in a slightly different form. It's just a little cleaner for this example. If I do the apex to apex map. So I'll do the velocity at the nth apex versus the velocity at the n+1th apex. Okay, that's the line of slope 1. And it looks something like this. Okay, off here, if I have theta dot equals 0 at the apex, that's my, I went up and balanced like a pendulum. If I had theta dot less than 0, that's not even well defined. I wouldn't have reached the apex. So sort of the dynamics are undefined over here. And I can only have a positive velocity when I'm walking forward. If I reach the apex, I got some positive velocity, and I want to see what the velocity is on the next one. Here's my rimless wheel simulated on rough terrain. Okay. And the deterministic dynamics, of course, this is a fixed point, and I will iterate through and come to this fixed point. It's a stable fixed point, right? And there's another stable fixed point standing still, but at least locally and with a huge basin of attraction, a stable fixed point. Okay, so now I'm changing it a little bit, right? Now I choose the ramp angle. Choose gamma, which is my ramp angle. And what that gives me now is instead of this deterministic apex to apex map, every time if I'm at some current velocity, right, I have an entire distribution of possible next step velocities, right? So maybe the picture you should have in your head is that where before I I knew for sure that if I came in with this velocity, I'd leave with this velocity. Now I've got an entire distribution, if I can sort of cartoon it around here, right? If I come in with some omega dot naught, or theta dot naught, then I'll leave with some distribution. So, there's some probability of leaving with the original and with anything less than or greater than that, right? And everywhere along the map, right? I've got now a stochastic return map. Does that make sense? I come in with this, and I draw from a Gaussian distribution to figure out where I leave, right? And I propagate it through the nonlinear map, which is the map. So it's not going to come out as a Gaussian necessarily anymore. And the question is, what does this dynamical system do? What does the dynamics of that distribution look like for my now walking robot making contact with rough terrain being the source of uncertainty? What do you think? What's going to happen? I mean, you saw that animation. What's going to happen to the rimless wheel? What are the dynamics going to look like?
What's your process like? Are you Gaussian around a fixed slope?
Yeah, I'll put the mean at a comfortable ramp angle that gave me this nice stable. Yep.
So I would imagine that I would kind of approach that equilibrium point where it's hitting the apex. But also, I could imagine the situation where eventually, like, it wants to go up a ramp and then it stops, and that happens, like, that stopping process kind of happens for any point individually. So I guess Gaussian kind of like falls off the edge, and you're left with the final condition being that it's just resting there.
Spot on. That was perfect. Yep. So I'll say it back again, right? So probably if I were to look at time, I don't know, 20 or something, there's a reasonable chance that it's near the comfortable rolling fixed point, right? The distribution will probably converge to the vicinity of this fixed point, maybe some Gaussian-ish thing, okay? But there's always some tail in this Gaussian, right, where it doesn't quite, there's a big enough step where it doesn't quite get over, or a couple small steps that just add up to it losing energy, enough energy that it can't make it over the top, right? That means there's some small leak on every step of it going to the standing still fixed point. Right, so on every step I'll have some chance of just ending like this, and this is an absorbing state. Once I enter this state, I will never return. Okay, so if you have an absorbing state, which can be reached with non-zero probability in a stochastic process, then the only stationary distribution will be the long-term behavior means if you look at the rimless wheel at time equals infinity, it will be standing still somewhere on your terrain. It will eventually have gotten unlucky and it will be standing still. Right? So you could take that as you could just mic drop and walk out of the room now saying, there's nothing left to do in walking robots. There's always, as time goes to infinity, my robot will always be falling down, right? So, you can do the best controller you want, but it's eventually, a Mack truck's going to come down the road and hit my robot, and there's some small probability that it's going to be down on the ground later, so there's nothing left to do in control. But I'd like for you to not do that. I'd like for you to be interested at least in trying to keep it alive as long as possible, yeah? And we're going to have the tools to do that. But it's kind of fun to watch how these distributions evolve. So let me actually animate the master equation for you, animate the distribution for you. See if I can make that a little bigger. Okay, so this is the rimless wheels return map. I'm doing a numerical approximation of it. I just did a histogram, so it looks a little messy as it converges numerically, but it starts off with some delta function at random initial conditions, okay? And it comes to this, this distribution around the fixed point. But if I were to let that go longer, that thing is slowly sinking as the tail of the distribution is slowly giving probability to the standing still fixed point, right? And eventually there's just no chance that the robot is going to be walking still, right? It's sad but true. I think any realistic model of a robot that can't get back up is bleak. Right, but here's sort of a fun sort of animation of it. Okay, so here's the rimless wheel on known terrain. It just converges in the known way. Okay, if I put it on small, rough terrain, it walks for a really long time. You can build up a nice MATLAB animation. This is Katie Bill's artistry. All right. And you get these long-living distributions, okay? So we actually, in that work, we talked a lot about metastability and trying to examine the stability of that long-living but not actually stable distribution. There's a name for this, right? So stability of this system makes me only focus on that absorbing state. But the dynamics of this are metastable in the sense that there's a long-living distribution that is sort of the second eigenmode of a linearization, okay, that basically is a long-living distribution that will very slowly go away. And if you want to try to control that distribution, then you have to think about metastability, okay? The name isn't important, but if it connects back, it's useful. Okay, so that's sort of the metastable distribution of the rimless wheel. That's a system that's fundamentally discrete. I think the noise, is actually fairly natural to describe in that. And it plays out exactly like we were just talking about. Okay, so that's one of my favorite examples. All right, so the feedback you guys have given me have always and forever told me you don't like it when I go into philosophical discussions. You'd rather see examples. I'm still going to give you a little philosophy here. This is sort of, I think we have to decide. You could say that I should be worrying about stochastic optimal control or stochastic analysis for every one of my robots. Every one of my robots has noise, right? But the question is, when does it actually matter? When do I have to think about all this stuff? When is it worth going through the extra complexity about reasoning about the distributions instead of just reasoning about the system as a deterministic system? Right? I mean, I guess the subtitle should be, can't I just do feedback? Isn't it sufficient to just make a system as stable as possible and in a deterministic sense? And then shouldn't that somehow describe what the stochastic system should do too? And of course they're related, but there's times where the strategies you get, and if you've seen a couple of the robotics seminars recently, you'll I've seen many examples of this, where the strategies you get from explicitly reasoning about the stochasticity are fundamentally different than the strategies you get if you just try to be robust in a feedback sense, right? So I think the high-level bit for me, I think the right way to think about feedback design on a deterministic system, feedback is trying to be robust to initial conditions, right? If I'm trying to make a feedback controller, that recovers from many different initial conditions, then that's really the problem. Is I'm trying to control the dynamics of my system for many, many initial conditions. So the question is, when is that a good approximation to noise, right? So my fun way to say this is that, I think if disturbances are sort of rare, right? So for instance, if someone just kicks me every once in a while, right? That's a rare disturbance, and that really does sort of look like a short-term change in the state of my robot, but then after, nobody's even listening to me, they're watching Big Dog now, right? So that looks like an impulsive change in my state of my robot, right? And then the dynamics are largely my model dynamics or my deterministic dynamics as I converge back down. And so really, having designed a good, robust feedback controller is sort of good for rare disturbance. A rare disturbance is sort of like someone just put me in a new initial condition and I started. But something different changes. I think if the rough terrain case is actually fundamentally a different case, where now the dynamics of the disturbance, what the difference between that is that now the dynamics of the disturbance are really happening at the same time scale as my convergence, right? So it's really about the time scales. If you if your stochastic input affects you at the same rate you're being stable, then somehow you can't ignore it. You can't just throw it away. These things will fundamentally affect the way you converge, and it pays, I think, it often pays to come up with explicitly robust methods for dealing with that uncertainty. Right? So I think for rare disturbances, yes, you can. If feedback is sufficient, deterministic, let's say, design. Is often sufficient. But for what matters is if the disturbances are somehow affect the dynamics at the same time scale as your stability. The same magnitude and time scales, right? But okay? And broadly speaking, there's a handful of ways that you can think about it in terms of control design. There's really, I don't know, there's a bunch of really good ideas, huge technical literatures, but they all fit into a handful of different bins, the ones that I'm familiar with and the ones that we use locally, right? So let's say that the first one maybe is not the most typical one, but it's the one I guess I cartooned on the way here in the intro slides here, would be I could explicitly try to control my distribution. Right? So I wrote down in the linear Gaussian case a new dynamical system, right? Which in general is it's got some dynamics, it's got some covariance, right? If I have a finite parameterization, of my distribution, then I can control it like then I can ask about its dynamics as an ODE. It's potentially a complicated, I mean, it's almost certainly a complicated one because, well, for instance, the covariance, even for a linear Gaussian case, always stays positive, right? I can't have a negative covariance. So you can tell it's not going to be there's not going to be a reasonable linear approximation of the dynamics of my distribution. It's going to be a nonlinear system. It's also, and this sounds self-serving, but I really think it's fundamental, I think it's hard because it's underactuated, right? Because think about it, even if I had a fully actuated robot to start with, so let's say I have n configuration variables, n actuators, right? Maybe my mean, already it's in state space, so it might be 2n, okay? But even if I could completely control my mean, I've just thrown in another n squared variables here, for which I don't have an extra n squared motors hanging around to directly control my covariance. So if I'm trying to simultaneously control my entire state vector in the mean and my covariance, I'd better have a lot of actuators to do that. I think probably not, right? So, so these things are destined to be underactuated. And I think that's fundamentally why planning under uncertainty has its own set of techniques, because It's hard. It doesn't work with the standard tools because it's underactuated. It's nonlinear and it's underactuated. But with the view from the course, I think most of the tools we've developed here can be applied to that representation of the system with some care. So for instance, the robotics seminar talk today, it was totally coincidence. I didn't plan it like this. It just happened that he was talking about planning under uncertainty. He was using trajectory optimization, just like we've talked about in class, where his target for trajectory optimization, he had costs and objective and constraints on the mean and the covariance of the process, right? And he just wrote down the dynamics of that process and chose control inputs that would do something, would minimize some objective using trajectory optimization on the mean and the covariance, right? And that's right out of the playbook, right here. I mean, he had cool tricks on top of that, but the fundamental approach of trajectory optimization to this nonlinear underactuated system is, I think, is in your playbook now, right? The reason it's not maybe the most common approach is because it's hard. Right? I mean, trajectory optimization will work, but in general, you have big planning problems, and people discretize, and you see people in the POM-VP literature. This is not necessarily a POM-VP already. I'm just talking about process noise here. Okay, but there's big computational efforts to try to understand how to solve that problem efficiently. Okay, but let's talk about the sort of more controlsy ways to do it, right? Roughly speaking, there's a lot of good techniques, good tools for sort of worst case analysis. All right, so if I have, typically this requires W to be bounded. Right, so if every Wn comes out of some bounded set, and I could then ask my system to be stable for all possible values of Wn, right? Stable's often tough. You can ask for it, right? But somehow you could ask for maybe or invariance, right? We said invariance, we talked about. So for instance, the common Lyapunov function tools we talked about before. If you can find a common Lyapunov function that proves that the system's always going downhill for all values of W inside that region, then you can say something about the stability of the system in a worst case sense. And it turns out you can also use that for control design. And he cooked up a nice SDP control design example for you for the problem set. Okay, but there's ways to do that worst case analysis and find controllers which somehow guarantee that the performance is provably good in the worst case sense. Another really big approach that we'll talk more about some of these here. Okay. Is sort of the average case analysis. Right, the worst case analysis is often criticized as being too conservative, right? So if you look at a gazelle running through a field, right? It's outstanding, amazing performance. Every once in a while it wipes out and falls down, right? And if you programmed your gazelle to provably never ever fall down, it probably wouldn't move as beautifully, right? You could argue that, and traditionally, robust control has been criticized as being too conservative in general, right? If you're really always thinking about the worst possible thing, then you're not going to enjoy life. You're not going to get high performance out on average, right? So there's a different school of thought which says I should formulate my optimization problems and just worry about my expected performance, right? And accept the fact that with some probability I might fall down, might destroy myself, right? So, and it turns out average case analysis works very beautifully with optimal control. So for instance, if we used to try to write our cost functions as just some additive cost, right? Now suddenly my cost is a random variable. So I could try to somehow minimize, I could pick a U trajectory that somehow minimizes the expected value of J. Right? So on average, I want to maximize my returns or minimize my cost. It happens, as we'll see, looks like probably next time, that especially in this additive cost structure, you can take that expected value right inside the Hamilton-Jacobi equation and come up with something that's pretty tractable to work with. And there's really nice tools for stochastic optimal control. Okay, and then there's one really other important one, I'd say, besides just worst case analysis and average case analysis, is maybe somehow in between the two. But I can somehow accept the fact that that noise will bounce me around and do bad things to me. But I'd like to somehow bound not the total effect that noise has on my system, but somehow the gain that has on my system. So the last one that has to be on your sort of high-level list of how to deal with stochasticity is, it falls under the domain of robust control for sure, but sort of via input-output gains. Okay, so the view you should have there is that you've got some disturbance coming into my system, and I've got some outputs, call it X, coming out, or it could be some subset of X, something that you care about. And the problem with the worst case analysis is even if I just throw in Gaussian noise, like we saw in our simple linear Gaussian system, right? The system is not going to be stable to the fixed point. If I look around at, V dot, I'm not going to be able to find a Lyapunov function that's always going downhill because there's always going to be some probability that's bouncing around at the origin at best, right? So what you instead might be able to say is that I just like, if there is some sort of total energy in my input signal, I'd like that total energy. I admit that that's going to show up in my output signal. If the wind is blowing hard, I'm not going to be able to stabilize myself to 0. But I'd like to be able to describe the deviation in my output as small compared to the energy in the input. I'd like to say I reject the power sort of in my input into something smaller on the output. So you think about these input-output gains. Okay, and we'll do a few explicit control designs here. So one of the most common ones is an L2 gain. So for instance, you could say, even over a finite time, let's say, I'd like to call this the power in my output. Some surrogate for power. It's the power in my input. And if I could somehow say that, for small inputs, I get small outputs. I'd like to, if I could make this somehow less than some number, if I can guarantee that the gain from input to output is small, then that's a different type of sort of certificate of robustness that you could give. And it's a very powerful one. And we'll have tools for designing that. You might try to minimize, common problem formulation is to sort of minimize my bound gamma. Right? That's L2 gain minimization. Turns out in the LQR, the extension of LQR to the L2 gain minimization is something we'll have reasonable algorithms for. Not closed form solutions, but reasonable algorithms. Okay, so maybe instead of diving into the first one of those, we're going to do that next time. Let me just, I know that was philosophy. Nobody likes philosophy, but really, I'd like you to think about, like, what would that mean if I was just applying this to this sort of system? Could I give an L2 gain description of this system, or what should I try to do? Or should I maximize the expected value? I mean, how would you try to shape these dynamics? If you're allowed to only change the potential field by a little bit because you've got limited control authority, what would you do to change it, and how would you describe what you want? Right? There's only a handful of things that we know how to write down to lead to tractable algorithms, and they each have different implications, right? So, and we're going to dive in. So, I don't know. Are there any questions at that level? Okay, I'm early for a minute for once then. Instead of diving into the next thing, we'll wait till Thursday. Okay, good. See you then.